Alrighty, welcome to part 2 of this series on stellar evolution. So last time we talked about the evolution of low mass stars and their natural endpoint as white dwarf stars. Now we're going to talk about the fate of high mass stars. So high mass stars actually do go through many of the same phases as low mass stars. These stars still fuse hydrogen in their cores while they are on the main sequence. A difference is that high mass stars will run through their hydrogen fuel very fast. So massive stars usually live on the order of millions of years, whereas low mass stars will live for billions of years. When hydrogen fusion in the cores of massive stars stops, we have a little bit of a problem. Unlike low mass stars, the cores of massive stars are so huge that when all the hydrogen runs out, not even electron degeneracy pressure can stabilize it. So the core of massive stars will collapse further, and it will kind of go through a cycle of fusing elements in the core and then fusing lighter elements in shells around the core, exhausting that element. The core collapses further and causes heating, fusion of higher mass elements, and kind of rinse and repeat, like going through this cycle kind of over and over again. The trend is for the star's surface to become cooler and become either a blue giant and later a red supergiant. But there are several oscillations between red giant and blue giant and back again that correspond to the fusion of heavier elements in the core of the star. So we have an example of an HR diagram here with the main sequence as this line. We have several kind of tracks, we call them, for lower mass stars, and you can see, they're kind of going through like a red giant phase down to the horizontal branch, the AGB branch. But we get up here for this is the higher mass star, the 9 solar mass star. It kind of leaves the main sequence, comes over to be a red giant or supergiant, and then just kind of comes back, and it does kind of oscillate, and depending on the mass of the star, it will oscillate between these two kind of extremes here several times before the life of the star finally ends. So as a low mass star evolves, we get a core of mostly carbon and shells of helium and hydrogen. Massive stars are able to generate more pressure and heat during collapse to fuse elements heavier than carbon. So by the time a massive star enters its red giant or supergiant phase, it has actually many layers. So a massive star kind of goes through an iterative process like a low mass star, but eventually ends up with several shells with progressively more massive elements can be fused. So we have a hydrogen fusing shell kind of at the top here. And then we have some helium, carbon, neon, oxygen, silicon, and finally an iron core. There might be some magnesium fusing in here too, but one of the important parts is we have an iron core right here. So iron is the end point. Under normal circumstances, stars do not fuse iron. Iron is the most stable element. So fusion up to this point is exothermic, meaning that it releases energy. That's how we're able to keep the star from collapsing against gravity. But for iron, it's energetically unfavorable to fuse because you need to actually add energy to do it. So once a star has a core of iron, that's pretty much it. So at this point, the star has a core of iron, and we have a problem because there are no more reactions in the core to produce heat. The core is degenerate, like that carbon core in a low mass star, so it actually doesn't need heat to keep it propped up against gravity. But it turns out that this degeneracy isn't enough because there is a limit, remember, to how massive an object can be to use electron degeneracy pressure to keep itself from collapsing. And that is 1.4 solar masses, or the Chandrasekhar limit. So if this core is more than 1.4 solar masses, it will collapse further. So this is the beginning of a supernova explosion, specifically a type 2 or a core collapse supernova. So low mass stars, if you'll remember, kind of gently pulsate their outer layers away, but high mass stars blast them away with an explosion. So in this situation, the iron core collapses rapidly, becoming even more dense. When the density gets high enough, the protons and electrons can combine to become neutrons. What was an iron core is now basically a big ball of neutron gas. When it becomes dense enough, a new type of degeneracy pressure steps in called neutron degeneracy pressure, and it provides the outward pressure to stop further collapse. Now we have what's called a neutron star, and this will happen to stars up to like 10 to 20 solar masses. Here we have kind of it's a famous the Crab Nebula, which is a supernova remnant, blasting out the outer layers in an explosion. This is a schematic of kind of what is going on. We have this very compact core right here. The rest of the star kind of falls in really fast and kind of bounces off the surface to come back out in an explosion. Right? The outer layers, they don't know when to stop, right? They don't know to stop. They don't know this neutron degeneracy pressure has kicked in. So it keeps falling until they hit that neutron star, right? They hit this new compact object. So this causes a violent rebound and shock waves that bounce outward. And that collides with the outer layers of the star that are still falling in, that haven't reached the neutron star yet. So the energy from this expanding wave can cause actually the fusion of elements heavier than iron. And in fact, supernovae are responsible for all of the more massive elements we find on Earth. All right, so that's what happens if you have a neutron star. What happens to stars with greater than 20 solar masses, right? Remember, that's pretty much the limit that a star can form a neutron star. So like white dwarf stars, neutron stars have a maximum mass, which is about 2 solar masses. More than that, neutron degeneracy pressure cannot balance gravity. So for really, really massive stars, neutron stars will collapse further and become a black hole. So let's talk about these two possible, what we call stellar remnants. So let's start first with neutron stars. So neutron stars are somewhere between 1.4 and 2 solar masses, which corresponds to like 8 to 10 solar mass progenitor star, and possibly bigger than that, depends on the situation. So these things are really small and extremely dense, right? If a white dwarf, illustrated here, is about the size of the Earth, the neutron star is about the size of a city. So a neutron star is down here, like this little pixel. But remember, it can be up to 2 solar masses kind of crammed into this tiny little area. So an example of how dense they are, the sun has about a density of 1.5 grams per cubic centimeter, a little more than water. A neutron star has a density of 10 to the 14 grams per cubic centimeter, which means basically a shot glass worth of neutron star material would weigh about as much as 1,000 cruise ships. Extremely, extremely dense. The surface gravity on neutron stars is also absolutely bananas. The surface gravity on Earth, right, remember, is about 10 meter per second squared, 9.8 to be precise. The surface gravity of a neutron star is 10 to the 12 meters per second squared, which is the equivalent to the amount of work you'd have to do to lift an elephant by 1 meter on Earth. So you can imagine how hard it would be to even stand up if you could actually like land on a neutron star. Neutron stars have a kind of an interesting history. They had been theorized for decades, but were discovered by Jocelyn Bell Burnell when she was a graduate student at Cambridge in the 1960s. She discovered a particular type of neutron star called a pulsar. Neutron stars tend to have what we call collimated jets of radio waves that shoot out from the axis of rotation. Um, these stars sometimes will spin extremely, extremely fast, like in milliseconds. If it's oriented just right, this can cause a lighthouse effect where we can detect very evenly and precisely timed radio signals. So you can get something that kind of looks like this, if this will go, right? Where we get a signal that you can really literally set a clock to. So when Burnell discovered these objects, there was nothing known in nature that could provide this kind of signal. So the joke was that these were alien signals. So she at first called these pulses LGM for little green men. They are, of course, not aliens. They are weird objects in and of themselves, but not aliens. Black holes, of course, are even stranger. We get black holes for stars above about 10 to 20 solar mass range for the progenitor stars. Um, they are infinitely dense, and famously, light cannot escape them. The escape speed from a black hole is faster than the speed of light, and since nothing can go faster than light in a vacuum, nothing can escape a black hole. So we know that neutron stars are held up by neutron degeneracy pressure, but we don't know a heck of a lot about the details of their interior, right, of neutron stars. But for black holes, we know even less. We just don't know what's inside a black hole. And I don't think that animation is going to work. Nope. Okay. Many times, these so-called compact objects, right? White dwarfs, neutron stars, and black holes are illustrated kind of like this. So according to general relativity, we live in this thing called space-time, and mass distorts space-time. The more massive and dense something is, the more it warps space-time. So you can kind of picture it like this, right? The sun, it distorts space-time a little. A white dwarf distorts it much more. A neutron star distorts space-time even more than that. And kind of the black hole is basically kind of like maximum distortion, right? You can kind of think of it as an absolutely a bottomless pit. There is an event horizon, which is kind of the quote unquote surface of a black hole. But we do not know what is behind it. Anything that is kind of inside this area can't escape. And so we simply don't know. Okay, so we are close to the end, but I want to step back and compare the HR diagrams for low mass and high mass stars. So for low mass stars, we have the HR diagram down here. They get much larger and brighter before eventually ejecting their outer layers and becoming a planetary nebula. The lifetime of these stars are on the order of billions of years. So remember, we have a main sequence star, less than 8 solar masses. It goes up to the red giant phase, down to the horizontal branch, back up to the AGB phase. Right here, it ejects its outer layers, becomes a planetary nebula with an interior white dwarf. High mass stars, on the other hand, live much more quickly, right? On the order of millions of years. And their path on the HR diagram is very different from low mass stars. They kind of oscillate in this space in a cycle of fusing heavier and heavier elements until they can't anymore and explode. So all of these tracks here are high mass stars, starting with 20 solar masses up to 120. You can see, depending on their mass, a 20 mass progenitor star will maybe go back and forth just a couple of times. But once we get to very massive stars, 85, 120, even 60 solar masses, we get a track that kind of really oscillates back and forth, almost like a scribble on the page. So this is the last slide. This is kind of my best way to summarize stellar evolution. So we have low mass stars, remember, less than 8 solar masses. That's what this M dot means. Low mass stars, during their main sequence phase, hydrogen fuses into helium. And when that is done, the star expands into its red giant phase. The star gets hot enough for helium to fuse into carbon, and then eventually there will not be enough heat to keep this going, and we get a white dwarf at the center of a planetary nebula. For high mass stars, which remember is greater than 8 solar masses, we have some similar evolutionary stages, but proceeds at a much faster rate than low mass stars. The pressure in these stars can create enough heat to fuse hydrogen, helium, carbon, neon, oxygen, and silicon in concentric shells with an iron core. Electron degeneracy pressure cannot keep the iron core from collapsing, which causes a supernova explosion. And depending on the starting mass of the star, the remnant will be a neutron star or a black hole. So I hope you see now why the HR diagram is so powerful, right? Where a star lies on the diagram will tell us what stage it's in now and how it will change in the future. So that's it for stellar evolution. Remember to read the chapters and take the reading quiz, and let me know if you have any questions.